I'm going to show you a very simple reaction, and it's an example of oxidation. Here I've got some magnesium ribbon, and I'm going to do an experiment that a lot of us have seen before, which is where I put it into a flame and let it react with the oxygen in air. And we get that really bright white light that we're quite familiar with. What we also notice though is that a white powder is left on the tongs and in the place of the reacted magnesium. This type of reaction is given a couple of descriptions. One of the most common ones is that it's combustion, so it's the reaction with oxygen, and that is exactly the right description for it. However, it's also an example of oxidation. And oxidation is a reaction where we notice the gain of oxygen by something or the loss of hydrogen of it. In this case, it was the gain of oxygen where magnesium reacted with oxygen to become magnesium oxide. Now, no, this is not a balanced equation. This is just quickly showing you the reaction itself. So the magnesium has had oxygen added to it. That's one of the reasons that we have this name oxidation. It's the gain of oxygen. Some reactions you'll notice that a hydrogen atom, or actually to be exact, a hydrogen ion is being transferred to something else. This is not an acid-base type reaction, but it is an example. So when you see hydrogen removed from something, it's often oxidation as well. But really, what it is a loss of electrons. So it's where the electrons have been transferred to something else. In this case, the electrons have actually been transferred to the oxygen atoms in the element. So they've gone from the magnesium to the oxygen. And that sort of makes sense when we think about the atomic structure, where magnesium is number 12. So it's 282 if I look at the Bohr assignment for electron configuration. So these two electrons can easily be transferred or given away or lost to the oxygen, which is number 8, so 2,6, and they'll both have the electron arrangement of 2,8, so a full outer shell, which will make them more stable. And that's why one of the reasons why this reaction happens so easily, and it's also highly exothermic as well. There's also another thing we're going to learn about later called oxidation number. And if you can assign oxidation numbers to things, you can use that as a quick way to gauge whether it's being oxidized or not. So the oxidation number of magnesium here is 0, and here it's +2. Again, we'll do that more at a later date. That number's gone up, and I've actually made a typo there. Planning ahead to another reduction. It's an increase in oxidation number. So, how can I show this loss of electrons as an equation? Well, what we do for oxidation is we write half equations. We show what is happening to the thing being oxidized. So as I said, this up here is not a balanced equation. It's actually quite an easy one to balance, but it's still a good one for me to show you how we do a thing called a half equation. As the name suggests, half equations are only half of the story. That's because whenever something undergoes oxidation, something else undergoes reduction. In this case, the oxygen is being reduced, but I'm going to do another video on reduction later on. So half equations are not complete. They have electrons in them, which shows the gain and loss of electrons. In the reaction we just saw with the combustion or oxidation of magnesium, the magnesium element is being turned into the magnesium ion in the form of magnesium oxide, that white powder that we saw on the tongs and on the surface of the unreacted metal. This one's quite an easy one to balance because, as you can see, there's one magnesium on each side. But what's not balanced here is the charge. The left-hand side has got no charges at all. The right-hand side has got a +2 charge. We balance the charge out by using electrons, and electrons have a negative charge. So I need to get both of them down to the lowest common number. Well, this one's 0 and this one's +2. So I need to reduce this side, the product side, down to 0 as well. So if I had 2 electrons, each of them with a negative charge, 2 minus 1 equals 0, and this side is also 0. Now there's some other common examples of this sort of thing. You could have just about any metal reacting will make its cation, so therefore they're balanced in the same sort of way. Sodium reacting with water, for example, makes sodium hydroxide. So it's going from sodium to sodium plus, Na to Na plus 1 electron to balance it out. There are some metals that have got more than one what we call oxidation state or oxidation number. A good example is Fe2+, which can actually be further oxidized to Fe3+. And again, I add the electron so that both sides have got a +2 charge. A common molecule that you'll work with this year is hydrogen peroxide. It can both be oxidized and be reduced. So this is the one I'm actually going to focus on for a moment now. H2O2, using my little rudimentary rules at the top here, gain of oxygen or loss of hydrogen, H2O2 can become water or it can become oxygen gas. Now, if it was to become water, it means it would lose an oxygen. So that's not one of these two rules up here. So that's not correct. Therefore, it must be becoming oxygen, which means it's losing its 2 hydrogens. Sure enough, that's correct for oxidation. Now, I can see that it's not balanced. Well, it doesn't make hydrogen gas as well, so I can't just go immediately and go, oh, O2 plus H2. Because I've got hydrogen atoms on this side and not on this side, the way that I balance them out is I use the hydrogen ion. So it actually makes H+, and it makes 2 of them, 1 for each of the ones in the original molecule. Now I look at the charges. This side has got a 0 charge. This side, due to the 2 hydrogens, has got a +2+ charge. So I add 2 electrons to balance that one out there. Now when I go into reduction, we'll start to see there's a lot more with this. A lot of the reduction half equations are very complicated. This year you'll tend to see that the oxidation half equations are actually quite straightforward. This is probably one of the toughest ones you have to do. And the hard thing really is deciding whether it's becoming oxygen or becoming water. And if you remember these as our 4 rules or things to look for, then that makes it easy. The final thing I want to just show you is notice that the electrons are always on the right-hand side in an oxidation half equation. That's because this is showing them being lost or given away to something else. So oxidation half equations always have the electrons on the right-hand side. So that's a way to know that you've got the loss of electrons. This is our key definition. And you might see some little analogies or, little sayings that go with this. For example, we often say, you can remember the things for oxidation and reduction this way. Oxidation is loss of electrons, reduction is gain of electrons, so they're opposites. We'll do reduction shortly. Or Leo goes Ger, losing electrons is oxidation, gaining electrons is reduction. So you'll often see these sorts of little things to help you remember. But the main thing I would say is we're looking for in an explanation that the electrons are lost when we draw the half equation, which explains why it's oxidation. As well as that, you're looking for these as signs that it's an oxidation reaction.